What are composite materials? Composites are a combination of materials that, when put together, don't compromise each other's quality or integrity. Instead, they enhance one another, providing structural advantages that improve the durability and performance of aircraft. Composites fall into two categories, fibrous and particulate. The fibrous variety consists of tough fibers embedded in a resin matrix. The latter type is composed of non-metallic particles, such as silicon, in a metal matrix, such as aluminum. In the early days of aircraft manufacturing, fiberglass was one of the most commonly used material.
Now let's talk about topic overview of composite materials. Composite materials have fundamentally transformed the aerospace industry, significantly influencing aircraft design and performance. Examples of composite materials in aerospace is fiberglass, carbon fiber, and armor fibers. Advantages of using composite materials is weight reduction, corrosion resistance, and durability. This is because composite materials is known for high tensile strength, lightweight, and high temperature tolerance. Composite material has been used in Boeing 787 and Airbus A350. Second is application in aircraft designs, which is in structural elements like part, wings, fuselage, and tail structure. And second is internal components like fan blades and casing to handle extreme temperatures while staying strong. Last but not least is future trends. Additive manufacturing is like 3D printing by revolutionizing production by creating lightweight and intricate designs with less weight. Second is next generation fibers. Materials like natural fibers and bioresin is used to reduce environmental impact while maintaining performance. This will support the industry decarbonization goals.
The history of aviation composite material dates back to the early 20th century, when the wood and fabric were commonly used in the aircraft construction. However, with the advancement in the technology and the need for the lighter, stronger, and more fuel-efficient aircraft, composite started gaining the prominence. In the 1940s, during the World War, the first significant investment in the composite occurred with the launch of the glass fiber composite. This composite product improved the strength and the durability compared to the traditional material. Following the development, the aviation sector started investigating the utilization of the composite material more jointly. Next, we go to the key milestone. At 1940s, the introduction of the fiberglass marked the first use of a lightweight composite material in aviation. Next, on 1960, the use of the fiberglass expanded to the helicopter rotor blades, demonstrating its potential in the critical aerospace application. 1970, carbon fiber began to replace the fiberglass in the secondary aircraft structure, leading to significant improvement in the strength and weight. At the 1918, the Boeing 737 features one of the first significant application of the carbon fiber composite in its horizontal stabilizer. At the 2000, the Boeing 787 Dreamliner became a landmark aircraft utilizing approximately 50% composite material in structure. The last one, 2013, the Airbus A350 XWB followed suit extensively using the carbon fiber reinforced plastic throughout its design.
So this is our example, which is the Lockheed Martin F-35 Lightning II, which is a multi-role stealth fighter using advanced composite for 35% of its airframe. This material reduces weight and enhances stealth by minimizing radar cross-section. So here are three of the many challenges that leads to the creation of Lockheed Martin F-35 Lightning II. So the first one is radar absorbent composite, which is the developing material to absorb radar signal for stealth. So Lockheed Martin created specialized resins and optimized fiber orientation. So second one is heat management. So high-speed operation generate heat that risks damaging composites. So engineers use heat-resistant resins and protective heat-splitting layer. And last but not least is electromagnetic shielding. So composite airframe can interfere with avionics due to electromagnetic interference (EMI). So hybrid composite with metallic meshes ensure EMI shielding while maintaining stealth and structural integrity. So now we are going to show you the three recent advancements and innovation. The first one is advanced carbon fiber composites. Modern carbon fiber composites feature improved resins such as epoxy and thermoplastics, enhancing durability, heat resistance, and fatigue performance. Nano-reinforced resins with carbon nanotubes are boosting strength to weight ratios, enabling ultra-light yet durable components for hypersonic and space vehicles. Second one is self-healing composites. This material repair minor damage autonomously using micro capsules of resins, extending structural lifespan without manual intervention. Innovation includes heat, light, or force-activated self-healing mechanism, critical for UAVs and spacecraft. NASA is studying them for radiation resistance, long-term deep space application. Last but not least is high-temperature ceramic matrix composites, CMCs for short. CMCs excel under extreme heat, ideal for jet engines and friction-heavy components, extending performance in high-speed operations. CMCs are being developed for turbine blades and spacecraft heat shields, tolerating over 2,400 Fahrenheit and thermal stress for re-entry.
Let's move to benefits and advantages. First of all is corrosion resistance. One of the best things about composite is that they don't corrode or rust like metals. This quality makes them ideal for use in environments where materials are exposed to water, like in boat and offshore structures. As a result, composite helps lower maintenance costs over time. Next is durability. Composites are tough and built to last even in extreme conditions like high pressure or temperatures. For instance, wind turbine blades made from fiberglass can endure harsh winds and stay functional for many years, providing reliable energy production. Last but not least is design flexibility. Composite can be molded into complex shape, which is a huge advantage for creating innovative products. This flexibility reduces material waste and allows manufacturers to optimize design for better performance, as seen in many modern vehicles and aircraft. Now, let's take a look at application of composite materials in aircraft industry. First of all, aircraft structure. Composite materials such as carbon fiber reinforced polymers are extensively used in the fuselage and wings of modern planes. These materials are much lighter than traditional metals, allowing aircraft to consume less fuel. For instance, the Boeing 787 Dreamliner uses CFRP for nearly 50% of its structure, leading to a 20% improvement in fuel efficiency. This innovation reduces both operating costs and environmental impact. Next is aerodynamics. Composites enable engineers to design smoother, more aerodynamically efficient wing shapes. This reduces drag, which is the force that opposes motion through air. With less drag, aircraft can achieve greater speeds while conserving energy, showcasing how materials directly impact flight efficiency. Other than that is jet engines. Jet engines rely on ceramic matrix composites for high-performance parts such as turbine blades. These materials resist extreme heat while being lighter than metals. This combination improves engine durability and boosts fuel efficiency, making flight smoother and safer. What about other industry? So, let's take a look at application of composite materials in other industry. First is automotive sector. In the automotive industry, composite materials like carbon fiber are used to make cars lighter and stronger. This helps improve fuel efficiency and vehicle performance. For example, one of the famous cars, which is BMW, use carbon fiber in some part of their cars to reduce weight without compromising strength. Next is energy sector. Composites such as fiberglass are used in wind turbine blades because they are strong yet lightweight, making them more efficient. They are also used in solar panel frames, increasing their durability and performance in harsh weather conditions.
Challenges and limitation. First, high production costs. The manufacturing processes for composites can be complex and labor intensive, leading to increased expenses compared to traditional material like aluminium and steel. Although the life cycle cost may be lower due to reduced maintenance needs, the upfront investment remains a significant barrier for many manufacturers. Next, complex manufacturing processes. Manufacturing processes involved in creating composite materials are often intricate. Techniques such as autoclave curing, resin infusion, and automated fiber placement require specialized equipment and skilled labor. This complexity can lead to longer production times and potential quality control issues. Last but not least, mechanical property limitations. Composite material can exhibit insufficient mechanical properties under certain conditions. For instance, they may be less effective in high temperature environments or under cryogenic conditions, where they can become brittle and lose structural integrity.
As the aerospace sector advanced into the future characterized by the continued innovation and the technological advancement, the pace of the aerospace composite is a push for the new era. This advanced material already essential to the compensatory aircraft design are the push for the revolutionary transformations that will not only redefine the way we construct aircraft, but also usher in a new era of efficiency, sustainability, and performance. The future of composite material in the aerospace is a push for exciting developments. First, sustainability initiative. There is a growing emphasis on the recyclable and the bio-based composite. This material not only reduces environmental impact but also aligns with the global sustainability goals by minimizing greenhouse gas emissions during the production and the operation. As advanced manufacturing technique, the adoption of the techniques like 3D printing and the automatic fiber placement is expected to streamline production processes, reduce costs, and enhance customization capability for the composite component. Next, smart composite research is underway to develop a film material that can automatically repair minor damage, thereby increase safety and longevity of aircraft structure. For the last one, hybrid composite, the combination of the different material is being explored to leverage the strength of the various components for the specific application like rotorplane in the helicopter.
Lastly, we will talk about conclusion. To conclude, composite materials play a crucial role in modern aircraft design by offering innumerable advantages that enhance performance, safety, and operational efficiency. Their characteristics, which is lightweight, superior strength-to-weight ratio, corrosion resistance, and design flexibility, have re-evaluated the industry standards. As aerospace technology develops over time, the strategic incorporation of composite will remain pivotal for driving innovation and ensuring that commercial aircraft meet future demands for efficiency and sustainability. The continuing development in this field promises further advancements that will shape the future of aviation engineering.